Welcome to part 2 of the ARSET training, NASA Satellite Laser Altimetry for Coastal and Nearshore Bathymetry. My name is Sean McCartney from NASA's Goddard Space Flight Center in Maryland, serving as your ARSET instructor. Wherever you are joining from, welcome. The following slides provide an overview of the two-part webinar series. So why would somebody want to take this training? Nearly 80% of the world's oceans are unexplored and unmapped. Successful coastal management depends on monitoring and mapping. Coastal bathymetry is essential for navigational hazards for vessel operations, tidal modeling and prediction, tsunami risk assessment and forecasting, underwater cultural heritage preservation, and environmental change monitoring. Satellite-derived bathymetry enhances capacity for collecting high-resolution, accurate depth data supporting varied applications. By the end of this two-part training, participants will be able to identify NASA bathymetry data used for global coastal and nearshore bathymetry mapping for risk reduction relating to shipping and navigation, identify the applications and limitations of ISAT-2 bathymetry data, or ATL24, for coastal and nearshore bathymetry mapping, plot and download ISAT-2 bathymetry data using SlideRule web client, and analyze ISAT-2 bathymetry data using the SlideRule Python client. The prerequisites for the training are 2 ARSET courses: the Fundamentals of Remote Sensing course and the Mapping and Monitoring Lakes and Reservoirs with Satellite Observations. From December 2nd to December 4th, there will be 2 1.5-hour sessions which will include presentations, demonstrations, and question and answer sessions. All materials and recordings from each session will be available from the training webpage. If you are not able to attend one part, a recording will be made available within 48 hours on the ARSET training webpage. Homework opens today, December 4th, and will be due on December 31st. A certificate of completion will be awarded to those who attend all live sessions and complete the homework assignment before the given due date. Part 2 of the training is focused on techniques for plotting and analyzing ATL24 coastal bathymetry. The objectives for Part 2 of the training are as follows. By the end of today, participants will be able to identify the applications and limitations of ISAT-2 bathymetry data for coastal and nearshore bathymetry mapping, plot and download ISAT-2 bathymetry data using SlideRule web client, and analyze ISAT-2 bathymetry data using SlideRule Python client. Please put your questions in the questions box and we will address them at the end of the webinar. Feel free to enter your questions as we go. We will try to get to all the questions during the Q&A session after the webinar. The remainder of the questions will be answered in the Q&A document, which will be posted to the training website about 1 week from today's training. It is now my pleasure to introduce the guest trainers for today's webinar: Dr. Christopher Parrish, Joseph Paul Swinski, Gretchen E. Mahori, and Kiana Keefe. Dr. Parrish is a professor of geomatics in the College of Engineering, School of Civil and Construction Engineering at Oregon State University. He also serves as director of the Geospatial Center for the Arctic and Pacific, a university-led advancing research and education in geodesy, geomatics, and geospatial engineering. He is past president of the American Society for Photogrammetry and Remote Sensing. Prior to joining Oregon State University, he held the position of lead physical scientist in the Remote Sensing Division of NOAA's National Geodetic Survey. He also serves as an affiliate faculty member in the Center for Coastal and Ocean Mapping Joint Hydrographic Center at the University of New Hampshire. J.P. Swinski is a 24-year NASA Goddard software developer who spent most of his career creating flight software for spacecraft and science instruments. He led flight software development for the Atlas instrument from 2010 until 2016. In 2018, he transitioned to cloud-based data processing solutions, and in 2020, co-developed SlideRule with the ISAT-2 project scientist and University of Washington, a public web service providing fast cloud access to ISAT-2 data. Gretchen Imahori is a staff scientist and SatBathy project manager at NOAA's National Geodetic Survey. With 26 years at NOAA, she supports hydrographic and remote sensing operations. She holds a Bachelor of Science in Chemistry from State University of New York, Buffalo, and a Master of Science in Earth Science Ocean Mapping from University of New Hampshire. Kiana Keefe is an analyst programmer with 2+ years experience working in Chris Parrish's research group at Oregon State University. She has a Bachelor of Science in Computer Science from Oregon State University. She is a lead developer for NOAA's comprehensive bathymetric LiDAR uncertainty estimator, SatBathy, photogrammetric shoreline uncertainty estimator, and a contributing developer of NASA's ATL24. Chris, over to you.
Okay, thanks, Sean, and hi, everyone. Again, my name is Chris Parrish. I'm with Oregon State University, and I'm really honored to give a demo on ATL24 and how we're going to use ATL24 and Sentinel-2 spectral imagery alongside each other for bathymetric analysis and also maybe looking at bathymetric change. So to set the stage for this, if you're going to follow along with me, there are some things that you need to set up ahead of time. So first of all, there are a couple of files that you should have been able to find on the training website. There's a shapefile, which is called Hyannis AOI, and then there's also a Python script, which is called psdb linear-regression.py. So you want to go and download those two files. If you haven't already done so, you also need to set up an EU Copernicus account in order to be able to download Sentinel-2 imagery. You'll also need to download and install QGIS, also known as QGIS. That's free and open source GIS software that we're going to use in this demo. And then there's 3 sites that you want to go ahead and bookmark. One is the Copernicus browser. The second is the SlideRule Earth web client. And then the third is the NOAA Web Map Tile Service electronic navigational chart. So here's our project site. This is where we're going to be working for this demo. This is Hyannis Harbor in Cape Cod, Massachusetts. This is a site that is meaningful to me because it's actually where I started my career. At the very beginning of my career, I worked on a NOAA hydrographic survey ship, and this is where I first met the ship and where we spent a few weeks working before transiting down south. So just to kind of take a quick look at the site here, one thing that you might notice is that there's a lot going on. In terms of where we are, so this is on the south shore of Cape Cod. You can see in the image up in the upper left where we are relative to Boston. But in terms of things going on in the harbor, there are a lot of coastal engineering projects, engineered structures, some of them going back nearly 200 years, such as the breakwater, the original breakwater. We've also got a jetty, groin field, other shoreline protection structures. There's a dredged channel that's used by the ferry. And then there are also a lot of storms that impact this area, including a lot of times large nor'easters. So really a lot of different reasons why there could be changes to the bathymetry in the site and why we might be interested in monitoring the bathymetric change over time. And just to make the point that bathymetry in this area has been of interest for a long, long time, here we're looking at an 1894 U.S. Coast and Geodetic Survey chart of Hyannis Harbor. So quickly, this is the workflow that we're going to go through. We're going to start with just a visual analysis of our project site. We'll do that in QGIS, just to kind of gain familiarity with the site. Then we're going to go into the SlideRule web client, and this is where we're going to be able to view and download ATL24 bathymetry, so ISAT2 bathymetry from our new ATL24 data product that Lori talked about in the earlier session. And then we're going to integrate that ATL24 bathymetry with satellite drive bathymetry from Sentinel-2 imagery and generate final bathymetric data layers for visual assessment. Before I jump into actually doing the demo, there's one step that I just want to talk about briefly so that it doesn't confuse anyone when we get to this step. So there's going to be a step where we're going to do this integration of the ATL24 bathymetry with Sentinel-2 imagery. And the way we're going to do that, we're going to run a widely known algorithm known as the STUMF algorithm. This is actually going to parallel, in some ways, I think, a workflow that Gretchen is going to show later in demonstrating the NOAA SatBathy tool. I'll just say the version that we're going to do, it's going to be a little bit basic compared to what Gretchen is going to show. So we're not going to make use of some of the new elements such as compositing and the switching model and Acolyte and other things that Gretchen might mention. But for visual analysis, this should be a pretty good workflow. So we're going to start by generating what's called pseudo-bathymetry, or PSDB. And that's going to be the logarithms, the ratio of logarithms of two different spectral bands. We're going to use blue and green. And then in the next step, we're going to do a linear regression of that pseudo-bathymetry on ATL24, or regression of ATL24 reference bathymetry on this pseudo bathymetry. And that's going to give us the parameters of a linear transformation that we can use to transform that pseudo bathymetry to actual depths. So with that, let me go ahead and at this point and just start in on the demo. And the first thing we want to do is I'm just going to bring up QGIS. Again, this is free and open source GIS software. The version I've got is 3.40, but any recent version should work reasonably well. And I'm going to go ahead and just open a new empty project. And at this point, I want to navigate to those files that I mentioned were on the training website. And so hopefully you had a chance to download those. If you did, some of the files that you grabbed hopefully were the ones called Hyannis AOI shapefile. And in this case, I can just kind of drag and drop. I'm going to take the one with the extension of .shp, and I'm just going to drag and drop that right into QGIS. There you can see it opened up. The first thing I want to do is probably just change the symbology. I'm going to double click that to bring up the symbology, and I want to change it to just a red outline, something like that, and say, okay, so there's my project site. The next thing I want to do is, let's see if I can move that screen sharing box out of the way. Okay, the next thing I want to do is, just like usual in a GIS, I want to bring up some base map imagery. And so to do this, I'm actually going to bring up some Google imagery. If you haven't set this up already, what you want to do is you want to go into plugins, manage and install plugins. And that should pop up this list of plugins that are both installed and not installed. So in my case, you can see this one called Quick Map Services. That's already been installed. If you don't have that yet, you want to go to not installed, search for it in the search bar and install it. Because I've already got it, I'm going to go ahead and just close this. And then hopefully at this point, you'll see over here on the right-hand side of the screen, the Search Next GIS QMS. If you don't see that, the way to get that to pop up is you want to go into, you should be able to go into just Web, Quick Map Services, and Search Next GIS QMS. So in this box, I'm just going to type Google Satellite. And the one I want to pick is the one called Google Satellite Hybrid. And I'm going to say Add. So that went ahead and opened up the imagery for my site. And at this point, I can just kind of explore a little bit. I'll turn off the project site outline just so we can see what's going on. Here are some of those engineered structures that I've talked about, the jetty, the breakwater, and then over here we've got a grind field. There are also some private revetments that have been installed for shoreline protection. The dredged channel that's used by the ferry. And so, like I mentioned, just a lot going on and a lot of reasons why bathymetry in the site might be changing and might be of interest. So in terms of looking at existing bathymetry, one thing we might want to do at this point is go ahead and bring in some NOAA nautical chart data, ENC data. And so to do this, I'm going to go up here and click on Layer, Data Source Manager. And I'm going to scroll down here until I see WMS, that stands for Web Map Service, WMTS, Web Map Tile Service. I'm going to do that and just click on New. And I think I've already got this set up, but it shouldn't hurt. I'll go ahead and do it anyway. I'll call this NOAA Web Map Tile Service ENC. And then I'm going to need to put the URL in here. And to do that, again, this was one of the 3 links that should have been available on the training website. So it's actually this one here that starts with GIS chart tools. I'm just going to grab that whole URL and go ahead and put that in here and say, okay. It looks like I had already set that up. So it says, do you want to overwrite it? And I'll just go ahead and say, sure, overwrite. Okay, and then I can close out of this box. And then back over here, now when I scroll down in this browser, I scroll down to where I see WMS, WMTS, expand that, pick the one that I just added. Whoops, I want to expand it and expand it again until I see something called default 028 millimeter. And I'm going to right click that and say add layer to project. And that worked. It went ahead and popped up the electronic navigational chart for this area. So we can zoom in and look at what the chart soundings look like for this area. One thing we might see, I found this kind of interesting just in exploring the ENC. If we get close to shore and, for example, close to this breakwater here, you see that there are a lot of these rock awash symbols. But actually, it looks like in the very shallowest areas, maybe not a great density of sounding. So hopefully we'll be able to use ATL24 and Sentinel-2 bathymetry to get a good idea of what's going on in those areas. So with that in mind, let's go ahead and just jump into the next part of this, where I'm going to show you how to get ISAT2 ATL24 bathymetry. And to do so, I'm going to go to the next of the links that was shared in the demo in the training website. And so this time I want to go to the one that's called SlideRule Earth. That's going to take me to this website here. So this is how we're going to be able to get NASA ATL24 data through SlideRule and this web client. So I want to click on the link that says web client. It's going to pop up. I want to make sure, this is something that I sometimes forget to do actually. I want to make sure that I've selected the tab that's called ISAT2 Coastal Bathymetry. And then we're going to be able to just zoom into our area and take a look at bathymetry in that site. Before we do that, I just wanted to make a quick point here. So in picking out the site for this demo, I very specifically chose a site that was somewhat on the challenging side. So a mid-latitude site. A lot of times when you see people do satellite drive bathymetry or ISAT2 bathymetry, a lot of times we're focused on these very clear tropical waters where we just know things are going to work great. So I purposefully tried to pick a little bit of a more typical project site. But just while we're here, I do kind of want to take this opportunity just to show you what it looks like if we, if we were to select a site that was in a really, sort of amazing tropical area here. It looks like I thought I had a site selected, so I might have to do this kind of on the fly. So I'm just zooming in here on Turks and Caicos, and I'm just going to draw a project box. I'll do one maybe that goes about like, maybe something like that. And I'm going to double click and hit run SlideRule. While this processes, again, the reason I'm doing this is not our site. I just want to show what it looks like when we've got a site where here what's going to happen is when it gets done processing, we're going to see that it's selected all of the different track lines of ISAT2 bathymetry. And for a site like this, what we should see is that throughout the entire site, we've got really amazing bathymetry. I'll give this a second to just finish processing. Okay, there we go. So that worked, that came up, and we can see it found all these different tracks of bathymetry. And in any given track, I'm going to change the color scheme. I'm going to change it to this wool scheme. So any track that's within this site I'm going to see this really just nice bathymetric profile. We'll see the depths dropping off to greater than 15 meters, depending on where I am in the profile. I can pick another line. Basically, any line I pick, I imagine is just going to look like pretty amazing bathymetry. And in this case, another thing that I can potentially do here is I can go to this 3D view. And when this loads, if I can get this to work, what it should do is, oh yeah, there we go. I should be able to just sort of drag this up and kind of rotate this around and look at the bathymetry for that site in 3D. And in a case like this, I could have even made my site a bit bigger. In a case like this, you can imagine that we could generate a pretty good bathymetric DEM even without incorporating any additional data. Okay, with that in mind, let's go ahead and go back to requests. And now I'm going to go up to the site that we actually are interested in for this demo. So I'm going to scroll all the way back up to New England and to Cape Cod and to our Hyannis project site. So here we are. Here's our actual site of interest. I'm going to do the same thing. I'm going to draw a box. I can make it pretty big. I just basically want to make sure I'm covering the whole area. So I can do something maybe, I'll do something maybe about like that. And then same process before. I'm going to hit run SlideRule. It's going to go through and process. Again, it's finding all the tracks of iSat2 bathymetry. So this one, in this case, if you're to spend some time investigating these different track lines, basically what you'll see is it's not as amazing as when we were just looking at Turks and Caicos, but we do seem to have some pretty good bathymetry going through the harbor. And so I can, just try a couple different track lines. And so it looks like we've got some good bathymetry. This is all great. At this point, let's go ahead and download it. And there's a few different ways I can do this. One way, if I want a little bit more control, what I could do is I could go ahead and select these individual track lines one at a time. And I could click on this thing that says 3D view. Oh, excuse me, not the 3D view, sorry, that table. I could click on table. And when this pops up, at this point, I can actually edit the command that's shown here. And I can do things like I can pick exactly what parameters I want to export. I can pick different filters or do things in different ways. However, for the sake of this demo, I'm going to do things in an easier way. I'm just going to go kind of right in the middle of my screen. If you see this button that says export, I'm just going to go ahead and click that. And I'm going to choose an export format, and I want to make that CSV, comma separated values, and say export. And I'm going to go ahead and put this into the folder that I created for this training. So I created this G, Hyannis Harbor, ATL24 demo. I'll make a new subfolder that I will call ATL24. And I will put this CSV file right in that folder. Something I should point out at this point, because I was kind of, I wasn't very discriminate in picking out exactly what tracks I want. I just grabbed them all. That was the easiest way to go and grab the data. I am going to pay a slight price for that later, and I'll talk about that when I get there. For now, we're actually done in SlideRule though, so I can go ahead and close the web browser and get back over into QGIS and back to our project site. And at this point, since I just grabbed that ATL24 data layer, why don't I just go ahead and bring that into QGIS? So the way I'm going to do that is I'm going to click on Layer, and under Layer, I'm going to do Add Layer, and there should be one that's called Add Delimited Text Layer. So I'll click that. Now I want to just browse to find that file. So it's the file that I just created there. I'm going to go to the ATL24 folder, select that CSV file, and say OK. If I want, I can scroll along down here in the bottom and see the individual fields that came in that file. So all the different information, refraction corrected orthometric height. So all of the bathymetry has been refraction corrected. It's got a confidence interval. I think that's something that Lori covered in her talk, but basically the confidence and the bathymetry classifications. spot, granule, etc. Everything basically auto-populated. It said that my X field is longitude pH, Y field is latitude pH. I can go ahead and set my Z field to ortho_H. That's my Z. And I can go ahead and just say add. And at that point, I should be able to close this window. And if you can see all these orange-ish dots that just got added, that's the ATL24 data. If I want, I can change its symbol. I kind of like doing this as a blue dot. I think that looks pretty good. But there's my ATL24 data. So at this point, we're really doing well. I would make an observation here, though, and that is that even though this brought in a lot of ATL24 data, it still is kind of sparse in terms of, there's areas of the harbor where if we're interested in looking at nearshore bathymetry, all we've got is these individual discrete tracks. So this is the point where we want to see how we can combine ATL24 bathymetry with spectrally derived bathymetry from Sentinel-2. So to do this, I'm going to go to the third of the web links that were shared in the training website. And the third link is the one that's called Copernicus Browser. So I'm going to open this up. You'll need to create an account for this. It's free, so free to create an account, and then you'll have to log in. I happen to already be logged in, and you can tell that because it's got my name listed up here. But go ahead and sign in if you need to. Okay, so the next thing I want to do is just go over to our project site. So I'm going to scroll over to Cape Cod and to our Hyannis Harbor project site. At this point, I want to draw an AOI, and so I'm going to use this little polygon tool, and then once I select that, I want to grab the tool next to it that looks like the pencil icon. I'll select that, and I might scroll out a little bit, and I'm just gonna go ahead and digitize something. It doesn't have to be perfect, and it's okay if I make this a little bit bigger than what it actually needs to be. So I'll maybe do something and just finish it off like that. Okay, now we want to put in a date. And this is the point where you could actually spend a lot of time looking through the different dates, trying to find imagery that looks good, cloud-free, water looks reasonably clear. I'm going to do a little bit of a shortcut. I've already done some analysis, and I found a date that looks good. So I'm just going to go ahead and put that in. The date that I found is 2023, 03/20. 2023/03/20. All right, there it is right there. So it brought up that date. I want to make sure I'm in the Visualize tab here. And at this point, over on the right-hand side of the screen, I've got this download icon. So I'll click that download icon. And then here I want to click on the tab that says Analytical. And I want to be careful with the settings here. I want my image format to be TIFF 32-bit float. I want to change my resolution to high. I'm going to go ahead and keep the default coordinate system. And then I'm going to select 3 different images to download. I'm going to do true color, so that's going to be the RGB. And then I'm going to pick just 2 of the bands. I'm going to do band 2, which is blue, and band 3, which is green. And I can just click the download icon. So that should be saving them to my downloads folder. I can go ahead and open that up. There it is. It just downloaded. I'm going to say, I'll just do cut, and I'm going to paste this into the folder that I set up specifically for this demo. I'll do a new subfolder. My new subfolder will just be called Sentinel-2. Sentinel-2. And copying that zip file, I'll go ahead and extract all of the different images that are in that. Let's do. Okay, so that worked. It extracted all the images. I'm going to do one more thing. Just because these are fairly long and cumbersome file names, I'm going to rename these. The thing that says band 2, I'm just going to rename that to S2 for Sentinel-2 blue. The one that says band 3, I'm going to rename that to be S2 underscore green. And then the final one that's the true color RGB, I'm going to rename that to be S2 underscore RGB. So I've got those three different images, all renamed. At this point, I can get out of that Copernicus browser, and I can actually just, this is another case where I can just drag and drop these. So I'll just drag and drop those right in. Whoops. So it looks pretty good. Here I am back in QGIS. I've got my my RGB image up at the top. If I want, I can go ahead and take my ATL24 bathymetry and drag that up to the very top, so that we can see where the ISAT2 bathymetry is on top of the Sentinel-2 imagery. Okay, at this point, we're going to move on to the next step, which is that stump ratio that I showed you earlier in the slides. And we're going to create that pseudo bathymetry layer. So this is going to be the ratio of the logarithms of the two different spectral bands, the blue band and the green band. So the way I'm going to do this is I'm going to click on raster and then raster calculator. So that brings me up here to raster calculator. I'm going to create an output layer, and I want to give this a name. So I'm going to put it right back in my demo folder. I'll do a new subfolder called PSDB. Again, that stands for pseudo bathymetry. And that denotes the fact that we're not going to have actual depths. It'll just be sort of pseudo depths or pseudo bathymetry. So I'm going to go in there and I'm going to make my file name. I'm going to do sdb.tiff. So I save. And then the next thing I want to do is I just want to go ahead and create that stump ratio. So this is going to be natural log of 1,000 times the blue band, so S2 blue, in parentheses, divided by natural log of 1,000 times the green band. So this might look a little funny. What is this? Again, this is just the stump ratio that we saw earlier back in the slide. So we've done log of blue over log of green. That factor of 1,000, that's just a constant that is designed to keep the logarithms positive and linearly related to depth. So I'm just going to go ahead and run this. I'm going to say okay, and it worked. It already generated my pseudo bathymetry layer. All right. The next step I want to do at this point is, like I mentioned earlier, our ultimate goal here is we want to use the ISAT2 bathymetry from ATL24 to calibrate our pseudo bathymetry. And so to do this, we need to create a layer that has both values. We want a layer that has the ATL24 heights. I should have mentioned, by the way, in the ATL24, the heights are orthometric heights based on the EGM08 geoid model. So those are actual datum-based heights. And then the pseudo bathymetry, that's not. Those are just sort of relative values. But what I want to do is create a layer that has both of those together. And so to do this, I'm going to go up to the processing toolbox. I might need to go processing toolbox. I've already got this up. So in this search window for the processing toolbox, I'm going to search for clip raster by mask layer. Clip raster by mask layer. And in this case, my input layer is going to be, let's see, I want to do, I want to do, oh, it looks like I made a mistake. I called the thing that I wanted to be pseudo bathymetry, I actually called SDB. That should say PSDB, but that's okay. My input layer is going to be just my SDB layer, and my mask layer is going to be, wait, I'm sorry. I see what I've done. I've done the wrong tool here. The tool that I actually wanted, sorry, back in this search box, the tool that I want here is the sample raster values. That's the one that I meant to bring up, sample raster values. So my input layer is going to be my ATL24 data. My raster layer is going to be SDB. And again, I should have called that PSDB. I'm going to create an output column. I'm going to call that sample underscore PSDB, and just go ahead and run that. And I can close. And that ran, and that created this layer called sampled, which now that has all the ATL24 heights, and it also has the pseudo bathymetry. So at this point, we're actually really close to being able to generate our final SDB layer. We just need to do a linear regression in order to calculate linear transformation coefficients that are going to allow us to transform our pseudo bathymetry to actual bathymetry. So to do this, there's a Python script. I'm going to go plugins, Python console, and then open up the Python editor. And there's this script that's, for me, already open. But if you don't have this open, you just want to click on the open script, and you want to browse and find the script that was made available on the training website. It's the psdb linear regression.py. And go ahead and open that up. That will open up the script. The only thing that you should actually have to change here is if you go down to this, it's line 7, and you'll see this path to where that CSV file lives. That you created. Again, that's the CSV file that we need, the one that has the ATL24 data and the pseudo bathymetry. You want to change that to your path and make sure you've got your slashes going in the right direction. And at that point, you should just be able to hit this green run script icon, and hopefully this will run. And okay, so that went ahead and that finished running, and it gave me the scatter plot. So what I see here is on the x-axis, those are my pseudo bathymetry values. On the y-axis, that's my iSat2 bathymetry from ATL24, and then it fit a linear regression line. The first thing I want to note in this case is that our R-squared value is actually fairly low. So we've got an R-squared of 0.54. Usually in my research group, we wouldn't move on with using this for bathymetry unless we had an R-squared of about 0.7 or higher. The reason that I happen to know that this is okay in this case is if you'll remember that there was that step when we were in the SlideRule web client, and I said that we could have been a little bit more selective in just picking out exactly which tracks we wanted to download, but we didn't do that. We went ahead and just sort of grabbed everything. So I know, because I actually tried this, that if I'd spent a little more time in that step of grabbing just the tracks that I knew had the best bathymetry, and or if I'd done a little bit of cleanup afterwards, I could get a much better R-squared value here. But actually, it doesn't really change the parameters of this linear transformation, the slope and intercept constant. So that's what we're really interested in here. So we're not going to worry too much about the kind of lowish R-squared. We just need these the values, the slope and intercept constants. So at this point, we are actually very close. This is a point where we're going to go back into raster calculator. Let me see if I can do it this way. I need to keep the scatter plot up because I need to be able to see these numbers. So I'm going to go back to raster calculator. And what I'm basically going to do is I'm just going to apply a linear transformation that is going to transform my pseudo bathymetry to actual bathymetry. So I'm going to do an output layer. I will call this, I'll create a new folder here that's just going to be called SDB. And I'll give this a file name. And because I accidentally called the other one SDB, I'm going to call this one, I'll just do something like SDB final, SDB final.tiff. And I'll say save. And now I'm going to create an equation to compute this, and it's going to be, I'm just going to look over here. This is why I kept the scatter plot up. I want to look at the two constants. So I'm going to do negative 25.850 times SDB, which really, again, that should have been our pseudo bathymetry, minus, oh, I'm sorry, not minus, plus 21.530, where those two constants, again, are just from over here in our scatter plot. I can say, okay. And it looked like that went ahead and ran. So I've got a layer that's now called SDB final. I do probably want to clip that to just our project site so we can, and I can get rid of the Python script at this point. This is where I want to clip it. So this is the point where I actually want to do the tool that I started to show last time. I'm going to do this clip raster by mask layer. And I'm going to clip SDB final. And the mask layer is going to be the Hyannis AOI. And you just let that run. Oh, wait. Oh, I guess it didn't select it. Try one more time. Run. Okay, that ran. Now I can get rid of this one, and I can turn off that and that. And I've just got my final SDB layer. And if I want to change the symbology, I can double click it. I can change from single band gray to single band pseudo color and just pick out a color ramp. I kind of like this one. This one looks kind of like bathymetry. And go ahead and apply and close. And so now I've got a bathymetric DEM for this project site. And that was created using the combination of iSat2 bathymetry from ATL24 and Sentinel-2 values. It looks pretty interesting. I can clearly see the dredge channel through there. I can see some of the deeper areas, like in the anchorage behind the breakwater over here. I can see some of the really shallow areas that are closer to shore. So everything looks pretty good. So at this point, if I wanted to, if I were interested in bathymetric change and kind of seeing how the bathymetry in this site changes over time, I could just repeat that process using multiple dates, multiple epochs of Sentinel-2 imagery. And then I could do differences of the DEMs or just sort of look visually at how bathymetry in this area is changing over time. So that's it. That's the end of the demo, but I just wanted to say thanks. And if you want to reach me, my contact information is here, christopher.parrish@oregonstate.edu. Thanks.
Chris, thank you for the excellent demonstration of ATL24 integration with Sentinel-2 and generation of bathymetric data layers. We will now transition to JP Swinsky, who will provide a demonstration of SlideRule Python client. JP, over to you.
Okay, well, thank you. I'm going to be talking about SlideRule Earth again. And just as a refresher from what we talked about a couple of days ago, SlideRule is a public web service with REST-like APIs for processing and accessing science data. And specifically, what we're talking about here is accessing the ATL24 bathymetry data. Last time we talked about the web browser, and I gave a demo of that web client. Today, we're going to be talking about the Python client that typically runs inside a Jupyter Notebook. And I'm going to be giving an example of how to access the ATL24 data from a Jupyter Notebook using the SlideRule Python client. Now, before I do that, though, I want to just show our landing page of our website. So the Python client can be a little intimidating. It's not as easy to use as the web client. And so we provide a lot of documentation to go along with it to help you out, to help you get started. So if you navigate to slideruleearth.io in your browser, you'll come here. And the first thing I want to point out is this contact us page. So you should always feel free to reach out to us. Here's this email here goes directly to me. I'm always excited when users email us, and we do our best to get back to you as soon as possible. You're also free for people that are a little bit more on the developer side. If you want to go to GitHub and open up an issue, if you find anything wrong or want a feature request, and certainly we're an open source projects and we invite collaboration. So you're also free to open pull requests and start discussions on features that you'd like to see. But now about the documentation. So clicking on the documentation link takes you to our documentation site, and this is it here. On the left, you can kind of walk through it in the order of which you would typically want to approach it if you're a new user. So getting started, the first thing you're going to want to do is know how to install the Python client. And this is instructions on how to install it. We support Conda and PyPy. You can also directly install it from GitHub. Then we have a really short, the simple hello world type Python program that can just get you started and make sure everything is installed correctly and you're running okay. And then we move into examples. I don't know about you, but I learn best from examples. So here's some examples that we've put together. And the one we're actually going to be going through today is this ATL24 example. But then as you progress, you can go through the user's guide. You're going to find out all the different parameters and APIs that are available. There's some more information for specific to ISAT2 right here. And then going down even further, we have our developer's guide. So if you're really interested in how this all works, we have a map of our project, why we developed SlideRule. Here's an under the hood. So here's an eye chart on all the different components and an explanation of those. But just wanted to let you know, this is where to go when you have questions about using the Python client. So now I'm going to switch over and actually look at our ATL24 example. So this is just I've checked out the repository and I've opened it up in VS Code. And so under the SlideRule repo from GitHub, I go to Clients, Python, Examples. And then under the examples, you'll find this notebook that I'm going to walk through right here. So I've set this all up. So I'm going to just run through this out. So this is, I'm importing the SlideRule client into my Conda environment. Oh, I should point out, this file right here is all of the packages you need to run all of our examples. You don't have to use it, but if you're wondering, man, I wish I had a quick way to get all the dependencies, this is what you'd use. Okay, so now I'm going to initialize the client. You will find one difference here. I'm running against a private developers cluster just so I don't pound the public cluster. This organizational setting is absent in the version that is on our repository, and it would go right to the public cluster. Here are some helper functions. I'm not going to talk too much about those, but you'll see them being used. It's really just to plot the data that we get back from the server. So I have functions to plot ATL24, ATL06, and ATL03. And now I'm also going to define an area of interest. It's just on the north shore of the Dominican Republic. And this is there are many ways that you can define an area of interest using our Python client. This is the simplest. It's just creating a list of lat longs. You can also use GeoJSON and shapefiles. But I've done this way here for clarity. So now if you just want, you just want all the data, ATL24 data in this area of interest. This is one line here. You run it. It's going to, it says that there's 110 ATL24 granules that intersect this area of interest. It ran in 8 seconds. It processed all 110 of those granules in parallel on the server. So just to talk through what's happening here, the Python client built a request when you hit this run, and it sent that request to the server. The server is sending back status messages, which we see displayed here, and then it sends back a data frame encoded as a GeoParquet file that the Python client then opens up. And so that's all what happened right there. And now I'm just going to look at that data frame, and it has 44,000 rows. That means it's got 44,000 bathymetry photons. And these are the columns that come back by default when you just do a simple access of the ATL24 data. So you'll see here that each photon has the same classification. It's all bathymetry. This is an encoding for which ground track it is. This is the height of the surface, the orthometric height of the surface. This is the reference ground track. If you know anything about ISAT2, all of the tracks are labeled. So it's reference ground track 758. Here's the orthometric height of each of these photons. So this has a depth of about 20 meters here. And here's the confidence level that the ATL24 algorithm assigned to it. This is which spot it was on the 6 spots of the ISAT-2 Atlas instrument. Here's the along track coordinate, or cross track coordinate. And then this source ID allows you to look up which granule the data came from. So embedded in the metadata of the geodata frame is a dictionary that links source IDs to granule names. And then lastly, this is which cycle the data was collected at. And we have the time and the lat long. And if you're familiar with geodata frames, this lat long is encoded as a point geometry. So let's plot this and see what it looks like. Okay, this is just a quick view of what it looks like. And so I can see here underneath where it's white, this is probably land. And then this is where we get a lot of good bathymetry near to the shore. And then the algorithm is doing its best to find bathymetry as it goes farther offshore. Okay, so this is a lot of data. Now let's say, you know what, there's actually a particular track that I'm interested in. And so I've pre-constructed this. So now instead of pulling all of the data, I just want the ground track 3, the right beam. I want the reference ground track to be 202, and I want it to be from cycle 12 of the ISAT-2 collection. So now let's run that. The client's going to construct a request, send it out to the server. The server's going to process that request and send the data back, and it happened now in 3 seconds. So I'm going to look at this data frame, and so now I've only got 861 bathymetry photons. So this set of photons is a subset of this one up here, and the subset is defined by these parameters here: the beam, the reference ground track, and the cycle. You can use others. You can include just one or include others that are in the data set, all of which are going to be explained in our documentation. Okay, so now let's plot this. Okay, so this is now a side view of the photons. Let's go back up here again. This is a top-down view plotting them, all of the bathymetry based on its lat long coordinate, and kind of color coding it to show some depth. But now we're turning this on its side and looking at just one of the tracks, and we defined which one of those tracks are, and we get this nice plot here. So this is a profile of the sea floor. Okay, so now I'm like, oh, I really like this. I want to dig in and get more information about it. So now I'm going to do a detailed access of this single track. Similar to what we talked about a couple days ago with the web client, I'm turning the compact flag off so I get all of the data. I'm going to now say, I don't want the server to threshold on confidence at all. Give me all of the bathymetry, even if it's very low confidence, and then give me all the different classifications. So let's run this. It's going to construct this request. It's going to send it to the server. The server's going to respond with the results, and it just didn't. And now we have 35,000 photons. Again, the reason we have 35,000 photons, so now we have 35,000 photons. The reason we have 35,000 photons instead of the 800 some up here is because we're asking for all the photons, not just the bathymetry. So we're getting a lot of sea surface and unclassified photons. So let's plot that. And here you see it. So you can see the gray is the unclassified. This looks like land. And then we come down, there's a little drop to the ocean. And then we've got the sea surface in blue. And we've got that same track now in red in the context of the other photons. Let's look at this based on confidence. And you can see here we have a bunch of different confidence values spread throughout the bathymetry being identified there. Okay, so again, something that we talked about a couple days ago was using the web client, we were able to, instead of going directly to ATL24, go to ATL03 and use ATL24 to classify it. So this is a more sophisticated request. The ATL24 is run against the release 6 ATL03, so I have to manually specify that. in the request parameters. I'm going to ask for everything. Because this is an ATL03 request, I'm going to turn off any filtering based on its own confidence values. And I'm going to ask for the same beam, reference, ground, track, and cycle. So this is going to go out and grab that. We got that there. And so now this is all of the ATL03 data classified with the ATL24. You notice it's a bigger area here, and there's more data that wasn't used by the classifier because it was outside of a band considered outside of the band in which there'd be valid bathymetry. So that's why there's even more data now in ATL03. But I also want to point out back up here, we're going to get different fields. So now we get what the spacecraft velocity was at each of these photons. We get what the solar elevation is. See, we get the background rate, and we get the quality pH flags. These are all fields that come in the ATL03 product, but do not come in the ATL24 product. So therefore, if you want those fields, this is an easy way to get that data and overlay the ATL24 classifications. Okay, so now let's combine some features of ATL03 and again combine it with ATL24 to do some filtering at the ATL03 level. So here I'm going to do the same request as before, except I'm going to do two new filters. I'm going to say only give me ATL03 that has a high confidence according to the ATL03 algorithm. And the ATL03 has this classifier called YAPSE, yet another photon classifier, which gives a score based on the local density of the photon, how many photons are near it. And so I'm going to say only give me photons that have a high density. So this is saying filter the ATL03 with these parameters and then overlay the ATL24 classifications. And so we run that request and we get the data back. Took a little bit longer, a second longer, because it had to do some more processing with the YAPSE and the confidence filtering. And now we have much less photons than before. And we see, interestingly, we see some gaps here now where there were photons that were filtered out by the ATL03 filtering, but were classified by ATL24. And we do see, though, some more photons that were classified by ATL24. And then it cleans up all of this, all of the photons. If you look back up here, all of this stuff that was obviously not a surface reflection. Some of these filters very quickly cleaned up all of that. And here we're now taking the same plot and we're overlaying, color coding it with the YAPSE score. So you can see what the YAPSE score is of some of these photons that were identified as bathymetry. Okay, so here's now a final step to this process of using ATL03. And that is, we're going to take ATL03 data, we're going to classify it with ATL24 data, then we're going to specify to only use the bathymetry photons, and then we're going to run the ATL06 surface finding algorithm on it to produce an aggregated surface elevation of the bathymetry photons. And we're all going to do that on the server, making this request here. So this request is constructed. You can see I talked through what it's doing, and this is the magic to tell the server to use the ATL03 surface finding algorithm. And so it ran, it took 3 seconds to run. And now this is the data. We're going to get different fields in this data set because this is really now like an ATL06 product, but we've fooled it by giving it bathymetry instead of land ice photons. So we get, number of fit photons, we get the surface window, we get the misfit, the armus of the misfit, we get the slope here, and so forth. Okay, so now let's plot this, and we get a very nice smooth return of the sea floor. Now again, you may say, well, there's some things here that aren't right. You can go back and tweak the parameters here and say, oh, you know what? Let me get rid of low confidence photons, or let me do an ATL24 confidence level that's higher. I only want the really high confidence photons based on ATL24. And you can tweak that to get a very clean, but even just with these parameters, we've gotten a very clean surface that's easy to work with, and is only a handful, right? 81, right? This data set represents the same surface, but is much smaller and easier to work with. And then lastly, for power users that you just want access to the raw data, here's a request that does some different filters just based on ATL24. So again, now we've moved past talking about the ATL03. We're back to talking about ATL24 and some of the more corner case features that we support. This set here, I've just chosen to turn off the low confidence filter. You could turn on a night filter. Say you have an area of interest and you're just interested in bathymetry that was collected at night. Well, you could turn this on, and then we'll only return bathymetry accepted that was collected at night. Or we have a calculation of what the maximum sensor depth is for the Atlas instrument when measuring bathymetry. Sometimes we think the algorithm will find bathymetry beyond that sensor depth. But if you want to just reject all of that, you can turn this on and say, if the sensor depth is exceeded, turn it to false, and that way you'll only get photons in which the sensor depth is not exceeded. So let's take a look at this, and you'll see now fewer photons because we've done some filtering here. Just for completeness, I'll plot that there. Now, lastly, an exciting feature that we've just added is the ability to directly query for ATL24 resources from the client, just hitting the Python, just hitting the SlideRule servers. So these are requests that do not use CMR in order to query ATL24 resources, and therefore we expose some additional query parameters. So here is an area of interest. I'm going to build a polygon string from that. And now I'm going to make a request for ATL24 granules with this polygon. And I'm going to say, I want to have a maximum mean depth of 10 meters. So nothing should have a mean depth of greater than 10 meters. So only mean depths for granules less than 10 meters. And I only want granules that are collected in the fall. So there's an encoding for which season. Winter is 0, spring is 1. Actually, this is the I have that wrong. This is the summer. I only want to collect in the summer. Summer's 2 and the fall is 3. So I'll run this request. It's going to go out to the servers. It's going to make that query. And now this is all of the granules. I found 53 tracks, and it's returning the granule names with the beam that meets this criteria. We have mean depth, min depth, max depth, season. We have the number of bathymetric photons, and a few other things that you can look at. And then also now, if you want more information about a granule itself, we have an API that allows you to say, give me information just about this granule. And so we'll run that. It went out very quickly, ran out. It made a request to the server. The server queried our own database and said, okay, for this granule here, it has these beams. This beam was collected in the summer. Oh, there's no bathymetry in that beam. Okay, beam 3, it was collected in the summer, had 4 photons, and this was the mean depth, min depth, and max depth for that, and so forth.
Thank you, JP. Great demonstration for participants wanting to explore the SlideRule Python client. Next, we'll hear from Gretchen and Kiana, who will present on NOAA's SatBathy tool and integration of NASA's ATL24 product. Gretchen and Kiana, over to you.
Thank you very much. We're very excited to talk about our work today on NOAA's SatBathy tool and the integration of NASA's ATL24. To begin with, we're going to give a little background, talk about SatBathy and what SDB is and its importance, and then give a few examples from our SatBathy desktop tool. I'll run through a quick demo and then pass it off to Kiana to talk about our ATL24 integration and her demo. And then if we have time, we'll talk about the future of SatBathy. So NOAA SatBathy desktop tool version 3.1 is now official. This is the interface. The whole purpose of the SatBathy tool is to automate the creation of satellite-derived bathymetry. And I should say that this desktop tool is for NOAA internal use only at this point, but I will talk about the future of SatBathy in a bit. So for those that did not catch Chris Parrish's talk in the morning, satellite-derived bathymetry, or SDB, is an indirect method of bathymetric measurement. And while it is not the most direct compared to multibeam sonar and bathymetric LiDAR, SDB is more direct than the gravity-based bathymetry. But given that, why do we care about SDB? The example on the left or the right give a good example of why it's important. The top right image is the bathymetric LiDAR example from our group in the Remote Sensing Division in the National Geodetic Survey. And this is of St. Joe's. If you look at the lower SDB example that Dr. Rick Stump created, it fills in the gaps of the bathymetric LiDAR. So there are some uses for it. But what is satellite-derived bathymetry in detail? For our purposes today, in SatBathy, we use the method of using Sentinel-2 resolution of 10 meters and updated research from Dr. Rick Stump and Dr. Isabel Caballero. And I should note that all SDB methods can be grouped into three major categories. The first one is spectral SDB, spectral radiance. For example, radio transfer equation, or RTE optimization, RTE empirical, and band ratio. The second is photogrammetric, and the third is wave kinematics. For our purposes today, we're going to focus on the band ratio approach, which is based on a statistical relationship between reflectance and depth. And it often requires, but not always, which I'll explain in a little bit when we talk about our simplified calibration, requires a known depth data to calibrate. The compositing approach for the band ratio solution inherently removes a lot of the faulty data. So what we're asked a lot of times is, why do we need SDB? For our purposes at NOAA, it's for internautical chart updates, hydrographic survey planning and reconnaissance, change analysis, and to fill in bathymetric LiDAR gaps in non-navigationally significant areas. In the image below, that's an example from our NOAA chart. These areas of unsurveyed locations still exist in areas like Alaska. But I'm going to focus on the hydrographic survey planning and reconnaissance. The reason SDB is so important, is we've been using it quite a bit, is it's become a vicious cycle where hydrographic survey data sometimes doesn't exist. We need the data. And the hydro vessels need to collect the data. However, if they're in an area where there isn't any data to operate safely, it becomes very dangerous. This is where SDB has become very important, to provide some amount of data so the surveys can be as safe as possible. So my first example is of St. Matthews. St. Matthews is off of in Alaska, off the coast. And the ENC, or electronic navigation chart, while it does show some areas where there are rocks and areas of danger which a survey vessel like the Fairweather need to stay away from, we were asked when the NOAA ship Fairweather had to survey this area, if we could run the SatBathy tool to provide reconnaissance data. The pseudo-bathymetry red example is on the left, and it shows some areas that are not captured in the ENC current chart. This helps keep the NOAA ship Fairweather safe to the best extent possible. Another example is in Kotzebue, Alaska. That's in the northern part of Alaska. And if you can take a look at the ENC on the left, there's a lot of gray areas. That basically says there are no charted depths here. So you're basically working blind when you're surveying in this area. Very dangerous. Again, we were asked to run the SatBathy tool and to provide data that would provide some information on the bathymetry. What we found was not just the bathymetry, but channels, multiple channels, 2 channels to show that where they can navigate somewhat safely. So the next I'm going to run into the SatBathy desktop demo. So this is the SatBathy desktop tool interface. And I'm going to zoom in on our area of interest, which should be around the area of Miami. Each of these squares are the Sentinel-2 tiles, and I will select the tile that I'm interested in and zoom in further and draw the area of interest. You can also provide an AOI, that's a zip shape file. And then I'm going to select the project directory. Next, we're going to figure out what start date we want. So for the Miami area, it's relatively clear. In Florida, most of the year, except when there's hurricanes. We're going to go up to January. Do January 1st. And we'll do an end date of a couple weeks earlier. For the cloud cover, we'll just leave it as default as 20%. You can move it to 10% or less. Cloud shadows, we'll talk a little bit about that as we're processing some of the data. Snow and ice, you don't have to worry about, and I'll show an example of the no data cover, what I mean by that. So now we're set. We're going to search for the imagery. The little dial shows that it's searching. And while we're doing that, I'm going to talk a little bit about, oh, well, it's already finished actually. Okay, let's look at our search results. It's pretty quick. So this is what it looks like after the imagery is run through, and we can go through and select which ones are the least turbid, have the least amount of clouds. This is quite a bit turbid, so we don't want to use something like that. We don't want to use the stuff with all the clouds. I'll explain a little bit more about that. I'm going to go back to the first one. This looks pretty clear compared to this one. Looks pretty turbid still in this area. So go ahead and select it. In a perfect world, if we had more time, we would select ideally 6 to 8 images to create the composite. And I'll talk a little bit more about that. But in the interest of time, I'm just going to select one, and then I'm going to submit the scenes. The SatBathy workflow and composite product. Procedure. For a given area of interest, or AOI, multiple Sentinel-2 L1 scenes are collected and atmospherically corrected to remote sensing reflectance, or RSS. Red, green, and blue bands are used as inputs to the band ratio models, PSDB red and PSDB green, which stands for pseudo-SDB. In addition, turbidity proxies are specified in the red edge 704 band and the OC3-based chlorophyll A product. So this is the PSD red and the PSD green. These are the red edge chlorophyll. For each scene, individual pseudo-bathymetry layers are generated and then composited along the temporal dimension by selecting the maximum PSD value per pixel, representing the deepest, least turbid observation. The temporal index of this maximum pseudo-SDB is recorded and applied to extract corresponding values from the red edge and chlorophyll A layers, producing composite turbidity proxy maps. These composite products provide context for any residual turbidity and serve as inputs to the subsequent steps within the SatBathy processing chain. As I spoke about before, when you're selecting imagery, there are a few things you need to take into consideration. We want low turbidity, When there's turbidity in the water column, the calculated depth is going to be more shallow than the actual value. So that's important to know. We also want little or no sunglint. Sunglint, or the reflection of the sun off the water surface, obscures the ability of the satellite sensor to properly capture reflectance. And then C, little or no shadows due to clouds. Those are the dark areas here. Shadows cast by clouds obscure the final SDB product by overestimating depth values. And then D, little or no clouds in the AOI. We talked a little bit about that. The presence of clouds also affects the final SDB results by underestimating depth values. Snow and ice is another one. Little or no snow and ice. Snow and ice on or near the shoreline affects the final SDB results and also underestimates the depth results. So I'm going to see if it's ready, and it is. Process is incomplete. I'll take a look at our map results. As you can see, there is our items. Take off some of these. A little easier to see. So this is the PSDB red and the PSDB green. We're going to focus on the PSDB red first. So now I'm going to walk you through the simplified calibration procedure. There we go. So SatBathy's simplified calibration procedure, as you recall, I said you normally need the charted soundings or reference survey to help tie the PSDB down to have actual true depths in meters. So we're going to convert the pseudo SDB derived from spectral ratios into true depths into meters. This option is beneficial for areas where we don't have reconnaissance or we lack recent high quality reference data. And the relationship is defined by SDB equals M1, which is the slope, times PSDB minus M naught, which is the offset here, where M1 represents the slope and M naught represents the offset. Okay. All right, so the next thing I'm going to talk about is the offset parameter, or M naught, which is this item here. The offset parameter is selected by sampling a nearshore pixel at the land-water interface, which serves as an approximate local datum. It represents the PSD value at depth of 0 and serves as initial reference point for the relationship between PSDB and water depth. When tidal information is available, the offset parameter can be further refined with a known vertical reference such as local mean sea level. Okay, so we're going to take the magnifying glass to hover over these area along the shoreline. You'll see these values here will change. Through our research, we know that the PSDB offset range is between 0.93 and 1.03. We'll head towards the interior, not the channel. See if we can find something. Looks pretty good. Okay, so now that I've clicked the offset, it fills in automatically. We're going to do the same thing for the PSDB green. Flip this down to PSDB green. You can usually pick the same from the same areas. The range through research for the PSDB green offset is between 0.85 and 0.95. That looks pretty good. Okay, so now that's filled into the offset, so 0.928. We're going to go ahead and submit the parameters. Zoom out a little bit. Okay, so a little bit more. Slope parameters, M1. The slope M1 value is roughly indicative of how strongly light attenuates with depth in the water column. Higher attenuation, for example, more turbid or scattering waters, requires a steeper slope, while lower attenuation in clear water corresponds to a shallower slope. An initial value is provided based on the mean of slope estimates reported by publications from Dr. Rick Stump and Dr. Isabel Caballero, which derive the calibration parameters through the regression with reference LiDAR datasets and or charted soundings. Let's go ahead and select that off. Because the optical properties and water clarity can vary regionally, users can fine-tune the slope in plus or minus 5% increments to better match local water conditions. The adjustment is constrained within specific ranges, where the PSDB red is between 4.88 and 16.5, and SDB green is between 42.7 and 88.45. Supporting turbidity indicators such as the 704 red band, which is here in our ancillary products. There we go. So that's the red edge. This is our chlorophyll. Oops, there we go. Red edge, chlorophyll. Can guide this adjustment by providing context on prevailing water quality. For example, clear, moderately turbid, or extremely turbid. Okay, so now that we have that, we'll now have we should now have the SDB red and the SDB green layers now available. Okay, so now you want to do a quick check of the SDB red. Make sure there's no negative values. Looks pretty good. We're going to just stick to the shore between 0 and 5 because that's where the SDB red generally, where the limits are, and it works the best. And then the green, we're going to do the same thing. Everything from probably about 5 meters to on should be in the positive range. You just want to do a double check. That looks pretty good. Okay, so that's the first initial check on that. So the area in Miami has basically a low tide. This is optimal for SatBathy. So in this slide, I'm going to talk about the importance of tides in micro and macro tidal areas. These red points that we created represent the tide gauge stations, and their values are calculated through NOAA's VDatum tool by subtracting the mean low water value from the mean high water value for that station. The difference between the two values represents the tide range of that location. If the tide range is a meter or less, it simplifies things for SatBathy. This means, and NOAA is case dependent, in general, a tide adjustment is not necessary because it falls within the vertical uncertainty of SDB generated through SatBathy. When the tide range is larger than 1 meter, locations require a tide adjustment because the potential vertical difference between the tidal stages exceeds the inherent uncertainty of SatBathy. We'll talk more about this when we discuss the tide model. I'm going to go back to our tool. And I'm going to select the different options. I'm going to add the reference data. That's another way to kind of see if we're in the ballpark. So this is remote sensing, our remote sensing division topobathy data under the National Geodetic Survey. And that will show up when I select. There we go. So let me take off our interim product so you can see this. So this is a little snippet of our data, our reference data. And then I'm going to expand this because, okay, so the SDB red. So the auxiliary grid, the values are shown here. That's for the reference data. And I'm going to flip this to SDB red. And as I move across, you'll see that the numbers change. So I'm going to stick probably close to the shore. I'm just going to run around and see how close we are. So we don't anything like a half a meter is between is okay. That's roughly okay. Okay, we'll do the same thing for the SDB green. Oops. Again, we're going to go a little farther out for the green. We do sometime after 5 meters. We're just doing a cursory glance here. All right, so those values look generally okay. We're going to go ahead, and you can always come back and adjust it again. But we're going to go ahead and submit those parameters. So before I hand this over to Kiana, I'm going to talk about our motivation at NOAA for integrating the ATL24 into SatBathy. First off, it's an entirely independent reference data source. It's near global coastal coverage is ideal for us. Well, it has maximum depth ranges, which are generally quite comparable to 1 secchi depth, and occasionally slightly deeper. And the ATL24 actually tests confirm its suitability for SDB calibration and validation. So like I was talking about with the future of SatBathy, the reason why we're interested in things like near global coastal coverage is because we were asked to expand the SatBathy to not just create bathymetry just for United States, but to go globally to work with our federal partners and with Coast Survey. So the global coverage is very advantageous, as well as the accuracy tests to make us assured that we're using reference data that's suitable. So that's a really incredible option. And we are working on, although the desktop tool is just available for NOAA at this point, there is a public site that's in work now that's going to take advantage of the ATL24. So we'll talk about that hopefully in another presentation. Now I'd like to pass this off to Kiana to talk about her ATL24 demo. And yeah, thank you, Kiana.
Thank you, Gretchen. So we get ATL24 data in SlideRule using SlideRule's Python API, which allows us to request granular data from October 2018 to November 2024 when release 1 of ATL24 was published. In SatBathy, we use a greater confidence threshold than the default value of 0.6. And this is to prevent some false bathymetry that occurs, especially around the sea surface, where the bottom of the sea surface can get falsely identified as bathymetry. The ATL24 implementation takes the satellite-derived bathymetry photon data, and then it regrids that photon data into a 10-meter resolution raster to match the resolution of SatBathy. This is to make it easy for use with Brian Eater's validation code, which produces error analysis, heat scatters, and histogram plots for SDB red, SDB green, and SDB merged. These values can be used to validate results or can be used to recalibrate the shoreline. If we go to an example here, I have set up a SatBathy run that is very similar to what Gretchen showed us just a moment ago. I've got a similar area of interest selected. I've gone through the tile selection and calibration steps. And so now all you need to do to get ATL24 products is check this ATL24 comparison checkbox before you click Create Final Products. If you look at the terminal while this is happening, you'll see the request to SatBathy start to generate. It's going to return photons in a random temporal order just due to the nature of how SlideRule gathers the data. And so we do a sort on that data from oldest to newest. That way, if a photon shares a pixel in the final raster, it'll use the newest photon to generate that pixel's value. This can take a moment to process, so I will just go and take us to an already completed folder. So to get to your data, you're going to go into your output folder. You're going to go into the prod folder, and into the ATL24 subfolder. In here, you're going to see the error statistics, heat scatter, and histogram results for your SDB green, SDB merged, and SDB red. You're also going to have a data subfolder, and in here will both be the ATL24.TIFF raster that we use in SatBathy, but also a CSV file that contains all the photon data retrieved for this request. That way, because it is slightly lossy to generate the raster, you can access all of the ATL24 data, including any of those photons that didn't make it into the final raster. This ATL24 TIFF, for example, can be used to pull it into QGIS. I've already loaded the data just by taking the file and dragging and dropping it onto QGIS with a base map already loaded in. And then I've set the colors to go from shallow, which is a yellow color, to a darker color in purple. And we can zoom in and see these lines here are our granule tracks that relate to the photon data that we've returned. Just an example of what this output file looks like. We'll go ahead and look at the merged values. So in merged, we have error statistics. And so this will give you the median absolute error, the mean absolute error, the bias, and then the number of photons relating to that bin that we've done for the statistics. So from 0 to 10 meters, the bins are in 2-meter increments. And then from 10 meters onward, the bins are in 5-meter increments. Just because in those deeper values, you can see like 10, 6, and 1 photon returns. The returns just get smaller. This is an example of what the heat scattering looks like. On the y-axis, we have the reference data set, which in this case is ATL24. And on the x-axis, we have SDB merged, which is the SDB merged results from our SatBathy run. As we can see, there's fairly good correlation on this 1-to-1 axis, which generally means that the ATL24 data is validating the results from SatBathy. And then we can look into these histograms that give us an idea of how the photon spread is within those bins. Alrighty, and then that's my portion, and I'll pass it back to Gretchen.
All right, so thank you, Kiana. Now I'm going to give some major updates for, talk a little bit about major updates for the SatBathy desktop version 3.1. So as Kiana mentioned, we have the validation code, and that should be ready to show you in our actual data. So that's in our validation folder. We can see how we did. So let's take a look at the SB merged heat scatter plot. Let's look at this one. Okay, so this looks pretty good. This is the generally from, like I said, the 0 to 4 is the SDB red, so they get merged. The green SDB, which is from about 5 meters to looks like it's about a little over 8. So this aligns pretty well. The reference data set we used was, again, our remote sensing division topography LiDAR under the NASA Geodetic Survey in NOAA. We have a lot more data compared to the ATL24, but so you can see a lot of more data points, which is nice. So it looks like it lined up pretty well. So the items, the values we picked look like it was on. But if it is a little off, you would do adjustment in the tool. You could use the multiplier. Let's say the green was a little, the dark spot was a little below that line. You would do the adjustment for the green here, down here, and we'd probably do the minus. And you can always go back. That's the nice ability of the tools to be able to like adjust and recreate the products. It's a nice benefit. Okay, we go back to, so that's And then Hannah already talked about the histogram and the error statistics. I won't go over that, but it's very similar. And then I'll talk a little bit about the tide module. As I spoke about earlier, for areas like Miami and Hatteras, those are below 1 meter tide or water level. But for areas in Alaska that we've been working quite a bit, sometimes it can be 5 meters. So in these cases and other areas where we don't have information on tide, we can use the on-datum SDB composite product using the Visio tide model. So the workflow is as follows. We extract a Sentinel-2 scene gradual sensing time, query the tide model at each X, Y, T point, create gridded water level rasters at local mean sea level, and composite the water level rasters according to maximum PSV red or green. And then finally, we adjust the calibrated SDB red or SDB green products using the water level grid composite. So the examples that we have to the right are for Hatteras. That's one of our regular test locations to make sure everything was working correctly. Normally we already know what the tides are for Hatteras, but for places outside that don't, or we maybe globally that we may not know, it will be very helpful. And there is plans to update to the most recent of Visio. So going back to where everything is, if you want to access that, that's in the SDB composites folder. So if you see the local mean sea level and at the beginning of the TIF and the water level, I have that already up along with the final project SDB merged. So this is the SDB merged. This indicates deeper water here. And then the tide module, local mean sea level adjusted, that is the product for the Miami area. So resources going forward for folks that are looking for more information on SatBathy and actually the research that all went into it. These are papers with from Dr. Caballero and Dr. Rick Stump. And I really like to do a special thanks to the SatBathy team, especially Brian Utter, who's been a huge help for all their continued support. And thanks to NASA for allowing us to do this presentation and training.
Thank you, Gretchen and Kiana, for the terrific presentation and demonstration on SatBathy. The following slides provide a summary of the concepts covered in Part 2 of the webinar series. ATL24 can be integrated with optical bands, blue and green wavelengths, for deriving satellite-derived bathymetry. SlideRule is a public web service with low latency access to on-demand data products stored in S3. SlideRule provides on-demand processing next to the data for generating customized data products using parameters supplied in the user's request. SlideRule Python client can be used to access ATL24. SlideRule provides documentation for the Python client, including example scripts, user guide, and developer's guide. SatBathy is a hybrid web desktop tool created by NOAA for automating satellite-derived bathymetry. SatBathy utilizes 10-meter resolution satellite imagery from the Copernicus Sentinel-2 mission, Amazon Web Service, and Acolyte atmospheric correction processor. SatBathy integrated the ATL24 product as an independent reference data source. The following is a summary of topics covered over both days of the training. NASA's ISAT-2 carries a photon-counting laser altimeter named Atlas. Atlas provides near-contiguous, along-track sampling using 6 individual beams of green light at 532 nanometer wavelength, providing high vertical resolution. Every photon detected by Atlas has a latitude, longitude, and elevation associated with it. National Snow and Ice Data Center provides access to ATL24 data, metadata, and tools. SlideRule is a public web service with low latency access to on-demand data products stored in S3. SlideRule Python API can be used to access ATL24. SatBathy is a hybrid web desktop tool created by NOAA for automating satellite-derived bathymetry. SatBathy utilizes 10-meter resolution satellite imagery from the Copernicus Sentinel-2 mission, Amazon Web Service, and Acolyte. SatBathy integrates the ATL24 product as an independent reference data source. Before we transition to the Q&A session, I want to remind you there will be one homework assignment accessible from the training page starting today. Answers must be submitted by Google Form with a due date of December 31st. To receive a certificate of completion, you must attend all live webinars and complete the homework assignment by the deadline. You will receive a certificate via email approximately 2 months after the completion of the course. We want to thank once more Dr. Christopher Parrish from Oregon State University, J.P. Swinsky from NASA's Goddard Space Flight Center, Gretchen E. Mahori from NOAA, and Kiana Keefe from Oregon State University for their presentations and instructive demos. Below is the contact information for Chris, JP, Gretchen, and Kiana, along with links to the ARSET website and social media. If you enjoyed today's webinar, we hope you will sign up on the ARSET listserv to receive notifications of future trainings. And please follow us on social media for other relevant announcements pertaining to NASA's Earth Sciences. We will now transition to the question and answer portion of today's training.
Okay. Can you guys hear me okay?
Yes, Gretchen. Yes, we can hear you. Yes.
Thank you. I can start on the questions, starting with the question 19. Does that sound okay?
Actually, we start from the first. So we're going to jump into
I beg your pardon.
one. So yeah, so question one, when integrating ATL24 datasets from ISAT-2 for shallow water bathymetry, do you typically use machine learning approaches? If yes, which techniques are most frequently applied? Example given, random forest, convolutional neural network, XGBoost, etc. And why are they preferred over traditional methods?
I think that was my answer to that question. And then, sorry, my answer ended up in a couple different places on the screen there. That's a really active research topic. It seems like there are papers being published every month on looking at different machine learning methods for STB. So I would just point to a couple of recent review papers that were published on STB, and also we did a recent ISAT-2 bathymetry review paper that was by Zhang et al., just published this year, that contains a lot of references.
Hey, Chris, thank you so much. Question number 2, could you suggest some case studies where ISAT-2 ATL24 imagery has been applied for ecosystem monitoring or restoration projects? For example, coral reef mapping, seagrass monitoring, or coastal habitat restoration?
Yeah, I can take that one too. There was a paper by Lequelic et al. Mike Jasinski of NASA was also a co-author on that. Sorry, I was trying to pull up the exact reference for it. But that was a paper specifically looking at ISAT-2 bathymetry for benthic habitat mapping. And then our research group is actually currently looking at use of ATL24 for coral reef restoration site monitoring in the Florida Keys. That's in collaboration with Jen Dykstra at the University of New Hampshire Center for Coastal and Ocean Mapping.
Okay, Chris, thank you so much. Question number 3. If we are integrating ISAT-2 ATL24 datasets with multispectral remote sensing data, such as Sentinel-2 imagery, what are the best practices to improve accuracy? Which remote sensing datasets are most frequently used for this purpose and why? Are there any tips for pre-processing, filtering, or modeling that can enhance bathymetry estimates?
I can keep going because I put the first part of the answer in the chat, but maybe Gretchen or others will want to chime in here as well. So, and I think this was covered in part in Gretchen's presentation, but careful selection of the input scenes, trying to find scenes that avoid clouds, turbidity, artifacts. Compositing of several scenes can improve the accuracy. Robust atmospheric correction, which was a step that Gretchen mentioned. And then another thing that we recommend is performing accuracy testing using independent reference data where available, as shown in Gretchen's and Kiana's demos.
Chris, thank you again. Question number 4, will this work for the purpose of archaeological diving?
I can keep going, but obviously anybody else jump in at any time. Archaeological, marine archaeology is potentially a really interesting application of iSat2 bathymetry and ATL24, and it's one that I've heard mentioned in the peer-reviewed literature. To date, I haven't seen a published study dedicated to marine archaeology, but I know that, again, it's an area that people are interested in, and I think are maybe currently actively working on.
Very cool. I look forward to reading some of those papers when they're published. Question number 5, are iSat2 ATL24 datasets used for applications like natural resource exploration or disaster monitoring, such as tracking sediment deposition? And can they be applied in hydrocarbon exploration as well?
I can take just the first part of that, or the second part, I guess, on disaster monitoring. So a former student, Joan Herman, did an excellent study on use of solely satellite-based methods, so iSat2 bathymetry and spectrally derived bathymetry, for looking at hurricane change analysis. And in Joan's study, it was shown that we could actually see sort of at least broad patterns of spatial change. For example, moving sandbars that occurred due to the hurricane. I think the resource exploration, again, that's another kind of topic that I think people are interested in right now. It's one that I've certainly heard people mention. I don't have any studies to point to off the top of my head.
Well, Chris, thank you so much again. Question number 6, how does the vertical accuracy of ATL24 compare to standard single beam hydrographic surveys in clear water? Can I use ATL24 to validate or even correct my existing field data?
This one was also my response. And again, anybody else, any of the other panelists, please chime in. I was trying to answer some of the questions in the chat as others were presenting. My answer to this one, iSat2 is generally not as accurate as single beam or multi-beam echo sounding. We did a study of ATL24 accuracy, and that was just published in a paper in Earth and Space Science earlier this year. What we found from the ATL24 bathymetry, we had 8 different test sites. The RMSE of the ATL24 bathymetry was 0.68 or 68 centimeters using all points. And if we filtered by just high confidence points, it was 0.43 meters or 43 centimeters. So I think, half meter or better than half meter is really quite good for a lot of applications, but still not approaching what you can get from sonar.
Great, Chris. Thank you again. Question number 7. Did you use Sentinel-2 data instead of Landsat for the spatial resolution for the model? Does this improve the model?
We've used both. We've used both Landsat 8 and 9 and Sentinel-2. Both can be great sources of input data for SDB. The Sentinel-2 spatial resolution is a little bit better in the red, green, and blue spectral bands, which can be helpful.
Okay, great, Chris. Thank you. Question number 8. My area of interest is a coral reef with high morphological complexity, such as rough slopes, sudden drop-offs, and narrow valleys. Since the iSat2 laser footprint is roughly 11 to 17 meters, does it effectively capture these sharp changes, or does it smooth out the bathymetry too much for precise coastal mapping?
Yeah, that one again was a great question. And that's correct. The ARSET2 footprint is around 11 meters, and that can be a limiting factor in extracting really high frequency spatial detail. Something that's important is that the along track spatial resolution of ISET2 is quite good. Points in the along track direction and nominal point spacing is about 70 centimeters, so that can help in resolving features. But really, my main suggestion here is just investigate it. In several of these talks by JP and others, you saw examples of using that SlideRule web client. That's a really fast and easy way to go in and visually grab some ATL24 data for your site. And I would just start there in terms of looking at how good the resolution is and if it's going to support your needs.
Awesome, Chris. Thank you so much. Question number 9. When you do the change analysis when Sentinel-2, do you calibrate the reflectance with ATL again, or use the regression coefficient from the original calculation and apply it to all the Sentinel imagery?
My recommendation is if you're doing multi-temporal analysis, so change detection or something like that, where you've got input scenes from different times, I would, if at all possible, I would do the calibration separately for each epoch. But if you wanted to, you could start with the calibration parameters from the first epoch and just refine them as needed.
Awesome. Thanks, Chris. Question number 10. Data collection model for water turbidity based on size, weight, composition, settling rate, overlay with world currents and closest coastal impacts? Question mark. Does it need to include baseline turbidity levels? Possible to make moving animated data overlay? Over seasonal tidal and trade wind change prediction models for cumulative impacts?
My answer here was this sounds like an amazing tool. To the best of my knowledge, that's not something that currently exists. But if there are people who want to take the lead on developing something like that, I can see it being beneficial to a lot of different people.
Great. Thank you again, Chris. Question number 11. How can tide be applied or removed from pseudo satellite-derived bathymetry?
I'll give my answer here, and Gretchen or others may want to jump in. So regarding tide correction, if you're doing single scene STB, so you're not compositing multiple scenes, and if your calibration data are already referenced to a vertical datum, then your output STB are going to be inherently referenced to that same vertical datum as the reference data that you're using for calibration. And so for that reason, in that specific case, you don't need a dedicated tide correction step. And to kind of explain that, if you're doing a linear transformation from your pseudo SDB to SDB, and the transformation parameters come from something that's already referenced to a vertical datum, any kind of vertical shift, for example, due to tides, is just going to be inherently accounted for. The time that you do need a tide correction is if you're sort of compositing or pulling together multiple scenes collected at multiple different stages of tide.
Okay, Chris, thank you. Question 12, since the interest is in bathymetry, would we want to sample satellite data just after ice off to avoid phytoplankton that might be growing in the water column in the later spring and summer, which could mask that bathymetry?
Quite possibly, yes. I would monitor global turbidity or KD 490 data sets to try to find optimal times for optimal water clarity. That is generally going to be the driving factor, and whether you get good bathymetry or not.
Okay, question number 13. Does the stump approach only work with the ratio of the log of blue and green, or could other band ratios be applied?
Absolutely, you can do other band ratios, and I think this was shown in Gretchen and Kiana's talks. For example, there SDB green and SDB red. Those refer to respectively ratios of log blue to log green, and then log blue to log red. So those are both combinations that can be used, and really any other combination potentially as well if you're working with hyperspectral imagery, for example.
All right, Chris, thank you again. Question 14. Have you tried to compare your depth data or the data source being discussed against real-world bathymetry data products such as the NOAA Blue Topo, to assess its accuracy?
We have in that accuracy test that I think I put in the chat. That was a comparison against NOAA data. A lot of it was airborne SatBathy LiDAR data available on NOAA Digital Coast, and a lot of that same data is available in Blue Topo. For the next release, we're going to try to do an automated accuracy test using all of the Blue Topo, all the NOAA Blue Topo data. But the development of that is something that's still in the works.
Okay, thank you, Chris. Question 15. What quality criteria in ATL24 would you specify to filter out noisy data? Since I will be working with an inland water body, can you specify comparable quality criteria for ATL13 data?
For ATL24, we've typically recommended a confidence threshold. So one of the parameters is that confidence parameter. It was discussed in Lori Magruder's presentation that provides a confidence of the bathymetry classification. We've used a threshold of 0.6 as a good starting point for filtering out some of the lower confidence data, but that's kind of site specific. So you might want to sort of play around with that and fine tune it. The second part of the question is correct. ATL13 is the corresponding product for inland waters. ATL13 provides a lot of other parameters, but there is a bathymetry parameter. To the best of my knowledge, there is not a similar confidence parameter, but I would definitely encourage reading the algorithm theoretical basis document, which provides all the technical specifications for the ATL13 data product.
Terrific. Question number 16. How would you integrate the SDB layer with the point bathymetry data?
This may have been where Gretchen was going to step in. Does Gretchen or somebody else want to pick up the questions from this point, or would you all like me to keep going? All right. Not hearing anyone else.
I'm sorry, Chris, I was muted. Go ahead. I was going to pick up at 19.
Okay, all right. I'll turn it over to you. That's it. Integrate the SDB layer with the point bathymetry. I'm not totally sure I understand the question, but if it's referring to how do you take your pseudo bathymetry and then integrate that with the individual points from ATL24, that was one of the steps that I showed how to do that in my demo, just using QGIS, and basically it was using that sample raster values tool to have the pseudo SDB, and then just at each raster or each location of a ATL24 point to sample the corresponding pseudo SDB value.
Okay, question 17. What about the difference in pseudo SDB per S2 detector?
Yeah, I think that's interesting. One of my recent students, Ruth McCullough, looked at actually using small sats where you've got, each individual satellite has its own imaging sensor on it, and so you've got just differences between the different sensors. I think that's just I don't have detailed information other than I think that's a great question and most definitely an area for ongoing research.
Great. Question number 18. I've collected hydrographic survey data across my study area. How should I combine field-based hydrographic data with ISAT-2 along track measurements to create a more robust validation data set? What are the trade-offs between them?
My answer to this one, just in terms of things to consider, need to pay attention to differing spatial resolutions and accuracies. Differing datums can definitely be a factor when you're trying to combine data. So for data collected in the U.S., NOAA's vertical datum transformation utility, B datum, can be a really useful utility for that.
Great. Question number 19. Where can I access the SatBathy tool?
Okay. Yeah, right now the SatBathy tool is for NOAA internal use. It's a desktop tool, but we are working on a larger cloud effort, public cloud effort. This will incorporate lessons we have learned over the years as we've worked with NOAA's Office of Coast Survey for our reconnaissance projects with them and our other federal mapping partners. But I think Sean has my information on the slide. So folks that are interested, you can feel free to contact me for updates on our status.
Great, Gretchen, thank you so much. Question 20. The example in Alaska was fascinating. Have there been any studies looking at the efficacy of these approaches in polar regions in particular, given the challenges presented by snow and ice?
Yeah, that's a really good question. We have found that working in Alaska has been very challenging. And we have been trying to do, where possible, some parallel research along with the SDV reconnaissance operational work for NOAA's Office of Coast Survey. Alaska alone is challenging area, so there's more work needed there as well as the other northern areas and polar regions.
Okay, Gretchen, thank you. Last question, 21. I missed the definition of SDB_merged and SDB_red. Could you explain?
Hi, Gretchen. Should I answer this?
Yeah, Brian, thanks. That would be great.
Great. So SDB red and SDB green are the two products that are created from the from our SDB algorithm or SDB approach. We found that SDB red typically works better in shallow regions, while SDB green is more suited for deeper water. So SDB merged uses a combination of those two algorithms, relying on SDB red for the shallow water, and then transitions to SDB green for the deeper areas. More information about how that works can be found in some of the publications that were listed.
Okay, Brian, thank you. And thank you to everybody that asked questions, and want to thank everybody that attended today's training, actually both parts of the training. Today was the last day of this two-part webinar series. So for wherever you were joining from, thank you so much. We also want to thank once again our amazing presenters, Dr. Christopher Parrish from Oregon State University, JP Swinsky from NASA's Goddard Space Flight Center, Gretchen Imahorimi from NOAA, and also Kiana Keefe from Oregon State University. We also want to thank subject matter expert Brian Etter from NOAA for joining today to help as a subject matter expert answering some of the questions. And also want to thank Amy Neely from NASA Goddard Space Flight Center as well for her vision in having this training take place. So thank you to all the wonderful presenters, and we look forward to seeing you in the future at an upcoming ARSET training. Thank you.